Hi, everyone. This is Lorraine Herger. I'm going to introduce our next keynote speaker, who is Dr. Bushra Bukata. We've done a little switch in the order. Bushra's talk is entitled AI Computing Services for AI, Unleashing the Power of Deep Learning for Robotic Trends and Challenges. So Bushra is a senior manager in machine learning and an AI scientist at Amazon Robotics. And the focus of her talk will be around automated intelligent systems based on computer vision and machine learning. Given the velocity and the speed of the Amazon system, which many of us have experienced, I'm sure this will be a very interesting talk and show us some of the issues and the highlights of how Amazon is able to do this. Dr. Bukata has a very impressive resume. You can find this in the Symposium website and in the conference materials, but suffice it to say that Bushra is a recognized leader in her field. She's also been a very passionate and involved leader for women in STEM. She's active in the IEEE and SWE and Grace Hopper and at Amazon. So today, as I mentioned, Bushra will focus on robotic applications, the use of deep learning, and also on machine learning algorithms in the machine learning algorithm lifecycle at scale, which is a very interesting aspect of how you can use these services in a system that has the scope and size of the Amazon delivery system. If there's time at the end, we will take questions. So now I will turn this over to Dr. Bukata for her talk.
Thank you, Lorraine, for the nice introduction. Thank you. I would like to first address the IEEE Services Computing Conference and especially the Women in Computing and Services Computing for inviting me for this talk. And it's been a pleasure working with all of you at this point. Thank you again. And I'm seeing here that I did have my slides up, but somehow they're not showing again, but I see that I can, let me see if I can share my screen. Maybe that will make it easier. Okay, let me see. I do have them uploaded here. Okay, can you see my slides?
Yes.
Okay, they are loading. Okay, yeah, somehow they were up. I can see them on my end, but not here. Okay, let's get quickly through the presentation. So thank you again for attending this talk. So I'm going to try to make it now quicker since we lost some time with the technical difficulty. But so the topic today, I wanted to talk a little bit about how AI is really used in computing services or services computing. And I'm going to give an example. I have worked in different applications, but I'm going to give an example in robotics specifically because there are some very specific challenges there because it touches the cloud, the edge, and also data and challenges with AI and how really putting it at scale, it's where really services computing shines. So, so today I'm going to be first giving a brief overview on AI in robotics, and then I will talk about the machine learning data dilemma and where synthetic data generation could be actually could be of a great help and help a lot to advance that. Then I'm going to switch and talk a little bit about the AI ML life cycle and how it is deployed at scale and how it can be deployed at scale. And I'll give the example of AWS SageMaker ML lifecycle management. So the motivation behind using deep learning, it's actually grown quite a bit recently because of, we have deep learning algorithms are really, really powerful. And they're used across the board, from self-driving cars to virtual fashion try-on, to gaming, to architecture and 3D and so on. And obviously in robotics as well. Now, the problem with that is that the data is not always available, and you need to teach these algorithms, deep learning algorithms that are really data hungry as well. And this is what I call using ML for ML. So there is actually, there has been a trend going on in using deep learning algorithms to generate data for deep learning algorithms. And I'll give an example specifically in robotics that I've been working on for quite a bit right now. So just to give a quick overview here, robotics are used everywhere, obviously in automation, from automotive manufacturing to other fields, but specifically like in Amazon, there are robots that actually help deliver any product that customers, when they search and look for products and you want to get it delivered, actually there is a whole system in the back end that starts actually locating based on your where you're located and where you want the product to be shipped and where that product is located across the Amazon fulfillment center. And there is actually a replication of things that happen. And to just to give a scale of why we need robots in fulfillment centers, like a fulfillment center, think of some of these fulfillment centers, they're like 6 football fields. So they're huge. So even though you have all the humans really doing a lot of work, there are a lot of work actually that is repetitive. There's a lot of distances that need to be traveled by humans every day. And also there is a lot of here in terms of timeliness is very important. So robots here, and I'm giving here an example of robots that actually pick up, either bring like the ones on the right, they're called drives. They bring either these buckets or containers, or they bring something we call pods, where actually items, any item, let's say a toothbrush or a toy or a phone or whatever you are ordering online, they live in these pods, and then these drives, they go underneath and pick the right pod to bring into a human to pick it up and then move it along the process flow so that it gets delivered and then repackaged into boxes. So I will focus actually at some aspects of that. Now, when these items, they're picked up and put in boxes, those boxes, they're sent to what we call a distribution center. So they get decentralized and then they get dispatched right to the specific location. Let's say if you order something from New York, but the item is in Seattle, so the flow is going to go through a distribution center in Denver, Colorado, and then from there it gets shipped to and what is called Amazon Last Mile, which is AMZL, to be delivered to the specific address. So those distribution center, there is actually an additional need for robots, and these are called, and here I'll show you, this is a robot that actually picks up, so this is called robot-to-robot manipulation, where now we have not only robots that those orange and blue robots that actually now take the packages, not the pods, but the packages, and drop them into chutes, but really, and here I'll play it. So here you see a robot actually picking up from a conveyor belt and then place it into a robot so that it goes to the specific chute here. this manipulation by robotic arm has been traditionally done by a human, but there is, again, just to be able to fulfill the scale that Amazon scale has to deliver and fulfill that prime delivery of 2 days. It is the speed is of essence, and also the volume. Even with people, it's really it's huge. So really here, what I'm gonna talk about, as humans, we can look at the package. So here, the first task is really called singulation. So the robot has to identify which one of these packages it can pick up first, and that's because of the this area here. So it's called the end of arm tool. It has the suction cups, and it needs to have something flat, identify how much force it's going to put on it, so that it doesn't damage that box, and then deliver it, right? So that's the first thing. The second thing, when humans, they pick these boxes, they have a barcode on it. So this barcode needs to be scanned and identified so that the robot, the other robot, the small drive, when it comes to pick it up, knows which chute it's going to drop it to, because that's going to go into a specific truck to then be delivered to the end point. And then also it does have this communication. This is where the robot manipulation happens, where now the specific robot comes and knows which chute it's going to do. So all this information needs to be processed. Now, as humans, and I'll focus a little bit more on the singulation, and then there are more aspects to that, because that's a computer vision problem. As humans, we are very good at that, but with robots, we have to teach them. And with the advancements of AI and machine learning, especially deep learning, there has been a lot of advancement so that we can identify which package, the angle, the area. We can even identify if there is a damage or not. However, there is a problem. So for example, here I'll give an example of figuring out, for example, if there is a damage on the package, so that doesn't get picked up by the robotic arm, because if it has, for example, a liquid damage inside, that's going to be a catastrophe if the robot picks it up and then the liquid goes around, and then also it can damage the floor and the other robots as well. Or if the tape is ripped open, if there are pencils, the worst case scenario, like pencils. Now you can imagine like pencils all over the floor, the robotic floor, and also on the conveyor belt, and will stop actually that whole area. So those are identifying the damage and what type of damage is very important, as an example here. And as humans, we're very good at doing that quickly, but with using, like some automation, machine learning comes to the rescue, and deep learning comes to the rescue. However, with deep learning, we have a problem, which is the data dilemma, which what I call the kind of like getting the carriage before the horse, meaning in order for us to get really good results, we need a lot of data. But in order to get really a lot of data, we need to deploy the algorithms. But the algorithms need to have a specific accuracy, specific false positive rate, false negative rate, and so on before they get deployed, so that we can collect data. So then how do we really tackle this problem? So there are a few things, and I believe in the panel, there were also a few, and the talk before mine, there were discussions about using some techniques for AI to really tackle some of this data problem, which is kind of like transfer learning and so on. So I will talk about that a little bit here. So so here, this is where I call kind of like even machine learning for machine learning, or AI for AI, or in this case, deep learning for deep learning, using generative models. I will just go through this briefly. If people are interested, you can look it up. There's a lot of really good information out there on generative models. But the idea here is that really you build a model that can generate something new that you haven't really either you train it with very little data or some data, and then it generates something. And it's really quite different than the supervised learning, for example, where you have to give it a lot of example of input-output data, and then you try to come up with something or you try to model what is the function between, or the relationship between the X and Y in this case. This is an example of how generative adversarial network, for example, how it comes up with what it is generating that is close to what you want. It has a discriminator, and that's kind of like one of the tricks here. And then, but it has multiple representations, in a space that is called the latent space, and then you have different latent representations of, in this case, of an image. Again, I'm not going to dive too much into this, but if people are interested, I can give really good references for this. So going back to the synthetic data generation. So the synthetic data generation, in this case, we have boxes, we have polybags, we have different types of envelopes. They also come in different, not only they come in different shapes, and packaging also changes from one season to season. For example, if it is Christmas time, or if it is Prime Day or something, you have different labeling on it, or different type of tape. And also the bags and poly bags, they come in different deformations. So one way to do that was I used kind of like an environment called Blender, where you can generate these 3D meshes of objects, in this case, boxes, polybags, and so on, and put a texture on top of it. And then to simulate kind of like how the flow of one conveyor belt to another conveyor belt, how this chaos happens, that actually there is a really good physics modeling behind that. I'm not a physics-based person, but I work very closely with them to really simulate how these cascading of rigid bodies, in this case, fall. So this is a very simple simulation of how, after generating these boxes, we simulated kind of like how these boxes will fall on a conveyor belt, so that we are closer to reality. Now I'm going to go back to just show another type of, so let's say we have already all these boxes that was able to generate using Blender, but then labels also, it's another thing, right? So we have labels that need to be hidden. They need to be this shipping labels, so they need to be really simulated in a way that really mimic the real labels as well. So, and this is an example of how we are generating the labels. In this case, those either triangles or the rectangles or whatever is shown to really showcase that we can generate these different types of textures. Another one, which is, I talked about it, which is damage. So here, these are two examples of damages. The one here is a label has a damage, which means we cannot read it, and we want also to train on that to identify that type of damage. Or here, a cut. And those ones, again, the way we're able to generate them is really using some techniques of using really real data from the wild of different types of damages on boxes, and using that area and manipulating them using some other machine learning techniques and also computer vision techniques, and then using them as a texture on top of the boxes. And here, here again, for detecting damage, we need to identify where the damage is and the type of damage. So here, just the example of here, there is a bounding box that says, oh, there is a damage. This is a damage. This is a damage here. And I'm going to talk here a little bit about something, again, even when we do all these data generation using synthetic environments like Blender, doing this texturizing and so on, there is a problem though. The problem is with the images. When we, if I show here, the images are so vivid and they don't look real. So what I've done is using actually as transfer learning. So an example of transfer learning is using cycle GANs, where you can, here you have a zebra, you can transfer it into a horse into zebra, vice versa, or like a photo of Monet into just a regular photo, vice versa, or summer into winter. And these are really, really good techniques that can help enhance the quality of the synthetic data. And here is an example here. So this is an example of a scene that was generated, again, using Blender with that rigid body simulation distribution on a conveyor belt, and put in all the different types of textures. But they are this is a synthetic view. It's very vivid in terms of if we compare it to a real image, which is this one. This is an image. You have ambient light, you have light that's interfering, you have shadows. There are lots of things going on when you're in the wild, like in a distribution center. So we want to really mimic that. And here is using transfer learning to transfer this image into what we call augmented synthetic image that looks more real. So with that, I will stop here. It's just to give a flavor of here in robotics, how it is used. But really, the key challenge here is how it is used at scale and how it is deployed at scale. Because again, here you have lots of things that live in the cloud. You have the robotic arms that is at the edge. There's a lot of information that needs to be processed, and it needs to be processed locally. There's data that needs to be pushed. As things change, you need to keep updating the machine learning algorithms or the deep learning algorithms and other. Actually, there's a lot of pipelines of algorithms. It's not just one algorithm. So here I'm going to talk about the AI ML lifecycle. So usually, typically when you are trying to build an AI system or an ML system, you have to do some data preparation, augmenting data, synthetic data as an example, and then you build the model, and then you deploy the model, and then you have to keep fine-tuning it if there is a need. Like in this case, it could be the feedback loop from human in the loop, or it could be from another machine, or just the environment assessing that, and then an expert system that can make the decision what to do. Like in this case, the decision-making system is the expert system is really with the robotic arm of what to do, right? So, is the box damaged? Should I pick it up? Should I not pick it up? Which box should I pick up first versus next, and so on? And then the information I send to the drive so that it comes and knows to which chute it sends it to. And I did talk a little bit about the life cycle in terms of data preparation. There are different things here dealing with missing data, and that's like using synthetic data generation is one example of that. Depending on the type of data, you need to do also feature selection, extraction, etc. Model building, this is an example of how you split your data into training and testing and evaluation. Again, if you have a supervised learning, it's a different story, but just as an example here. And then you deploy the model so that you can do it. So now, to do all that, you need to have an environment that really can allow you to do it at scale. And here I give an example for AWS ML Stack. So there are lots of type of machine learning algorithms. I talked to you about the robotics application. There's like Alexa for speech. There's other types of vision applications like Amazon recognition and search. For example, whenever you do a search or when you are on the Amazon website, you're looking for an item to recommend. There's also recommendations. So there are a lot of things here. But really, there is the interesting thing is that how do you make an environment that is suitable for someone who is like me, like an applied scientist, who really wants to get all the complexity taken care of, while I focus mostly on really building the model in an environment that I'm familiar with. It seems very simple, but then it scales up pretty nicely here. And then also, like, there are lots of things that as an applied scientist, I want to leverage. There are a lot of libraries, for example, PyTorch or TensorFlow or MXNet. Then I want also to use, in some cases, GPUs or CPUs or use the elastic inference. And I want maybe to have some models in specific containers because they have certain dependencies, but because I have a pipeline, I need to manage those. So I don't need to manage those and have them at scale, right? Especially in deployment. So here, and I talked about this now, when we talk about the machine learning lifecycle, it's build, train, deploy, right? So in this case, you have a Jupyter notebook that you can build very simple intuitive interface. You can choose your IDE and then develop your algorithm, do some proof of concepts. Then once you're ready with it, you can push it for learning. Once you have data, in this case I gave for robotics, you can use synthetic data. Over time, you can use real data as it comes through. Of course, there is annotation. There was also talk about annotation at scale and how do you trust the data and so on and so forth. That's a different topic, so I don't want to dive too much into it, but that's part of this package for life cycle. And then you train, so you do the model training, but then the model training, there's also hyperparameter fine-tuning so that the model really becomes very powerful. There are ways of doing this also in an automated fashion in this new environments like AWS or Microsoft Azure, and I know others like IBM has some similar concepts, but again, since I'm with Amazon, so I'm just going to talk about that at this point. And then really deploying the model and then managing the deployment, meaning, hey, how is the model over time? Can I check how is the performance of the model? Is my model drifting? Then is my data changing? Do I need to retrain the model? Do I need to come up with some other models as well to enhance the models I have? So all that is part of the life cycle.
Bushra, this is Lorraine. I'm sorry to interrupt, but unfortunately, we're short on time.
Yeah.
So this is a fascinating talk because it's something we're all very familiar with as users. So I think we would have liked to have gone longer, but I think we need you to wrap up. Okay.
Sure. Yeah. These are the slide, the kind of like I'm almost in the last
okay,
here.
right.
So I'll go through this very quickly. So I will skip through these fundamentals, but I did talk about them, so we can check these. There are some nuances here, and I'll skip through this one because it's like this is just showing that actually it is nice to have this elastic environment where you, as a person, you don't see the complexity, but you have access to the data and all that, and it's all managed in the background. And these are different types of algorithms that could be used. But what is interesting here is that and this is where this type of platforms is important, is that you don't have to build everything from scratch. You can also leverage existing algorithms. Like there's a lot of open source algorithms. There are machine learning algorithms in the marketplace that you can leverage. You can put them in different containers and so on. And one thing that I really wanted to emphasize here is actually here, as a user of these environments, I don't have to really worry about load balancing my data, where my data lives versus where my machine learning algorithm lives. How do I expose these machine learning algorithms to an application that is hosted somewhere? So all this is an example of how you can use an Amazon API gateway to talk to a client application, and then you use this concept of lambdas, these functions that really helps with the pipelining, and it's really like very simple. Like you just write very simple code, but it gets translated automatically on your behalf into the complex system and manages it better. Let me just step through this quickly because this is an important concept. Is first, let's say you have deployed your algorithm. The problem is really not that, is that you want also to monitor how your algorithms and your pipelines are going. So this concept of configuring your data capture, not only where your data lives, but also the logs of how you are, how your algorithm or how your algorithms are really performing against the data you have or in the environment you have. And then here, as an example here, I think which is important, is that you can schedule these monitoring jobs. Like you don't have to monitor everything. You can, it gives you some flexibility to really pick which jobs you want to monitor, because sometimes, oh, I know maybe my environment changed, so I want to check specifically this algorithm because it's going to be highly impacted, or maybe I don't know, maybe I just want to monitor everything. So there are a lot of all these environments. They are getting very, very sophisticated because they have also machine learning scientists embedded in building these environments for us, which is great, I think. And obviously, like visualization of the results that you can analyze and see, oh, I need to add, or I need to retrain or build a new model or enhance my model and then redeploy. So with that, I will bring it to conclusion that actually this is a fascinating environment, and it's not, although I talked about robotics, it can be applied in different areas, as I said, in self-driving cars. I worked on, when I was at GE, I worked also on wind turbines and bringing the wind turbines with all the terabytes of data that they're generating every day, which is crazy. This is great. This is linking it to the Internet of Things, which was also mentioned during the panel. And I'll give like 4 key things, key takeaways here is that when we're looking at it at this point, is that what does mean data at scale? So integrating different types of data, managing all that in a very automated fashion, but also using machine learning and all the computing services computing to help with that as well, right? So there is data as a service as another example that was mentioned before, but that's another interesting thing. And then I did talk about a little bit about AI and ML at scale. How do you really maintain a model over time and all that, and how you maintain it? That is also, it's not solved problem. Those are still very much research problems that a lot of scientists are really working on automating the AI ML lifecycle. Security is a big challenge, as was mentioned in the panel. You have commercial clouds versus proprietary clouds. You have also privacy is the big challenge here, and how do you trust that these models that you trained, they're not biased, and also how do you trust that they're not hacked, so that the decisions, again, you're having all these robots now, and all these machines, not necessarily just robots. Turbines, for example, they're generating power for us, or self-driving cars, they're driving. How to ensure that they're not hacked into, and they're also not biased, so that the outcome is fair, and also it's secure. And then there was also a lot of discussion around cloud versus edge. Robotics is another really great example. All of these, actually, it's where you don't need to send all the data back. You need to have some processing power, for example, in the wind turbine or the self-driving car, in case the communication gets or the connection gets disconnected, or if you have some data that is sensitive, you don't want to send over, but you want to send maybe some high model of it or high representation of it. Data privacy is very important. Same thing for robotics, like all these shipping labels, they need to be redacted. We cannot send them for annotation. For example, if we want just a bounding box and human annotators to do that, we don't want them to see customers' shipping labels, or as we are taking images, there could be associates in the ground. We don't want to have their faces as part of this, because we don't want that, right? So with that, I will just leave you with the kind of like, this is a fascinating environment where I am with the robotic arm on the left, and I use some deep learning transformation to set me up in a more relaxed environment. Since I cannot be with you in person, I wish I could. We can socialize a little bit more at a restaurant. And here is my email address and LinkedIn connection if you guys are interested in. And with that, I'll move to questions.
Bushra, I'm not sure if we have time for questions, so I'm glad that you shared your LinkedIn and your email, because I'm going to encourage people, if they do have questions, to contact you directly. So I think with that, we're going to go over to our other keynote speaker, who is Valentina, who will be introduced by Ruchi.
everyone. My name is Ruchi Mahindru, Senior Technical Staff Member at IBM, and it's my true pleasure and honor to welcome and introduce Valentina Salapura, Dr. Valentina Salapura, who is a Principal Engineer at Google nowadays. And before becoming or transitioning to Google, she was a Senior Fellow at AMD, where she was working on distributed computing and supercomputing. And before at AMD, she was our colleague at IBM Research, where she focused on system architect, and her pioneer work is in IBM Blue Team, for which she received several awards, including recognition in 2006 ACM Gordon Bell Prize for her special achievements in Blue Team, supercomputer, and quantum chromodynamics. She's quite curious. That's quite demonstrated through her over 80 papers and over 400 patents. At IBM, she was honored continuously for many years through her tenure there as IBM Master Inventor. And before all of that, as a curious scientist, she started her career as a faculty member at University in Vienna, Austria, where also she pioneered research into her, where she invented this first application accelerators for fuzzy logic and artificial neural networks. So with further ado, I welcome Valentina to get us through the next topic. Thank you.
Thank you, Ruchi. Thank you, Ruchi, for this very kind introduction. I truly, by the way, of all those many patents, I collaborated with Ruchi on a number of them. Ruchi is quite prolific herself. Okay. I would like to thank the organizer for inviting me. Is audio okay? Yes, good. Okay. I would like to thank the organizer, and in particular to Kauta El-Magraoui, if I pronounced it well. I practiced to have me here, and I'm thrilled to be able to feel about how we are going through a revolution, and this is the true beginning of the era of computing, and I would like to share that with you. So before starting into what's new in computing, let's see some industry and technology trends and come to the problem that we are facing. So many of you have heard about slowing down of Moore's law, and for this audience, I'm not going to go in very deep detail of Moore's law, but many of you know that it has to do with scaling, with technology scaling, and that roughly as transistors become smaller, they become faster, and we can pack more and more transistors in the same area on the silicon. So that happens about every 18 months. We can pack twice as many transistors as before. And this is not really a law. This is an observation that Gordon Moore made while working at Intel in 1965. So that is more than 50 years ago. And we had a long and great ride with it, and technology made great progress over the time. And this is illustrated on this figure here, on this chart. So x-axis is time, on y we have exponential compute performance growth. So it tells us every 18 months we get twice as many transistors, which translates in compute hour performance roughly to we double the performance. And after 50-something years, that law kind of started breaking of old age. What is happening is, as we are scaling transistors and they are becoming smaller, eventually we are hitting this physics and laws of physics. How many atoms are there in any of those dimensions of transistors? And we are making them smaller, but we do not get any more the performance increase, the density of packaging, we do not get power efficiency. So hitting those physical limitations, this growth is increasing. It is still there. We are investing tremendous amount of tricks and solution, different materials, how to make those small and smaller new technologies still happening and continue scaling. But now it is, we are definitely hitting a plateau. So that is on the delivery side. So our ride we had for more than 50 years, it's kind of over for a while now. That is on the supply side. Let's see what is on demand side. On demand side, we have a different story. So here we have actually two lines. Blue is specking performance of processor over time. That is what most always delivering compute capabilities over time. Red is also exponential line, but it is a number of hours of YouTube upload of videos uploaded to YouTube over time. And that is just one example. Similar trend, as you heard the previous speaker as well, is in the data, amount of data, big data that is happening, and a similar pattern is appearing everywhere. Point being, we see that red line is significantly growing faster than the blue line. So demand is much higher than what we can provide in a supply. So we have this slowing supply, we have growing demand, and this is bringing us the problem statement that we are looking to solve. What do we do? Obviously, what we have done for more than 50 years has to be changed. We cannot continue doing what we are doing. And how can we still deliver the computing power and performance that is requested by our growing users with always new problems and increasing number of applications and increasing demand of compute capabilities. So that is why I'm calling this new era. What shall we do? We obviously cannot continue doing what we were doing. So we have to come up with something new, and that is actually happening for a number of years now. Did not happen overnight. It's happening probably for more than a decade, and it's increasing, accelerating in what's going on. And I think we are reaching a critical mass now. That there are some, if I may say, true computing revolution is happening, and we are here and can contribute and need to drive this exciting new era of how to deliver computing performance. So we have to think outside the box. And there are multiple different ways what this approach is being done right now. And the two main directions that I would like to highlight is heterogeneous hardware, meaning let's try to make more efficient hardware and use different type of hardware calculation to deliver compute performance we need. And the other one is let's try to use existing hardware that we have in a more efficient way so that we get more performance of what we have. So from the heterogeneous hardware, I'm sure you've heard plenty about accelerators, and that is let's use kind of various types of processing units which are smaller and faster and better fitted to a certain task. And combine them with other types of computing. And that level is happening at the chip level and also at the system level. More efficient use of hardware also has a couple of flavors which are evolving over time, such as software-defined systems and disaggregated or composable systems. And I would like to mention a theme or two which are kind of underlying for both of these approaches, and that is kind of huge demand by machine learning for more compute capabilities, and also need to deliver these capabilities at planet scale and to be integrated in the cloud. So let's first have a look at heterogeneous computing. As I said, that is computing when we are using more than one type of processing unit, and that is evolving around accelerators. So we are talking about specialized hardware, custom hardware. So if I have only one task to calculate only a certain machine learning algorithm or some different specific task, I can probably build a very small custom hardware, custom silicon that is going to be really fast. It's going to be small because it's not doing anything else but just that functionality. And since it is small, it's also going to be very power efficient. So that is what accelerators are. And how the accelerators are popping up, they're usually chips, they're evolving. You've heard about machine learning accelerators, video accelerators, data compression and data encryption accelerators, network offload, and so on and so on. So all various types of accelerators. I will talk about that more. There's another, talking about trend of heterogeneous computing, so using different types of computing, there's a different level of heterogeneity which is also appearing, and that is at the chip level. So instead of building a large chip which is doing everything, let's use small chiplets and compose multiple of those chiplets on a single substrate, building a bigger substrate, so that we can mix and match different functionality. A single chiplet is a tiny chip, which is very well-defined functionality, and it's small in area, so it's very well-defined and does well one thing, and we can kind of build multiple of those, put them like Legos, like Lego blocks, and design a bigger substrate, and then produce that bigger substrate with those chiplets, and in that way come to heterogeneity. That is another trend which is also currently pioneered by AMD and AMD research. I have to mention that. So let's have a look at those hardware accelerators. So CPU is central processing unit. That is what we are using, what we were using more than 50 years. Happily, every time a new chip comes, your program just works twice as fast without much changes needed for that. But for a number of years, there are GPUs, graphic processing unit, appearing, which are being increasingly used for various acceleration. FPGAs, field programmable gate arrays, where we can offload certain functionality on FPGAs and program them to do that functionality quick. Then TPU, TensorFlow Processing Unit by Google, for machine learning and data processing. WISC, vector compression unit, for YouTube videos that I mentioned, and other high-speed streaming data videos. Then we have a DPU for data processing unit, and then whatever special processing unit is needed for the application or du jour, which is killer application at the time, we can build and figure out how to offload that functionality and build a specialized silicon for that. And more is only coming. So what are we learning from here? That accelerators are gaining on importance, and that there are a very large number of those, and that specialized hardware it's just increasing in variety and complexity. So let me just mention quickly the TensorFlow Processing Unit by Google. It was first introduced, the first version in 2017, announced at ISCA. Then versions 2 and 3 were announced in 2022 at Hot Chips, and this is the presentation where you can find plenty of great technical detail and very interesting for Google AI. And just recently, Google released the TPU version 4 at the Google I/O conference. So that is the current kind of AI acceleration. And TPUs are used in Google data centers a lot. They are used for search. They are used also for ads and many other different applications in the Google Cloud. So this all sounds great, right? But it does not come for free. As you know, no good idea goes unpunished. It comes with certain costs. So what we are doing, we are trading off between increased performance and specialized calculation and loss on flexibility, because on CPU and general processing unit, we we are very flexible. We can run all of our software and calculate it. So we are losing flexibility. So we better be very correct and estimate, okay, how much of that acceleration will I need? How often do I need it? So we have to guess that ratio correctly. So we are losing flexibility, and also the software complexity to operate on both CPUs and to drive accelerators is increasing. So we have to account not only for kind of splitting the functionality when we are writing application, what will be run on CPUs, what has to go on accelerators, but also we have to account how data is moved between memory and these different various types of processing units. We have to take great care that this data stays coherent, that we don't kind of quickly run into various versions of data depending where it is being processed. We have to account for different programming domains. Accelerators usually have their own instruction set, and it's not only accelerators we are using, there are many other kind of programmable components within a computing systems like network interconnection, or there is recently a lot of offloading of computing and moving it towards the memory, like near memory computing trend. Also, if we have so much of data movement and different processing units working on it, we have to account for increased need for security, and that is also reflected in increased complexity of software. So all of a sudden, this is moving into becoming a hardware-software co-design problem, and we have to take care that this kind of balanced system that we are building, which has different types of acceleration, that it matches the best way our needs that we have for the application. Let's see about the second trend that I would like to touch, and that is how to use hardware that we have more efficiently, how to make better use of what we have. And for that, there are also multiple approaches. Let's start off thinking, how can we use the whole data center as a single computer? Google started to work on this many years ago, a couple of years ago, probably more than a decade ago, to see, having all those data centers of huge scale, planet-wise, how can these data centers be used as a single computer and optimize it in such a way that we can make the best performance, deliver the best performance for the workloads that we have to deliver. Apologies. So that is done in a way that we define that hardware blocks are created, which are then being managed by software. So software is managing efficient hardware blocks and creating those abstraction level of illusion that we have needed hardware and network resources. And of course, everything is managed by software, management software. But we can bring this to another level of having system-defined, software-defined systems, and that is to go one level beyond, and that is to break apart actually a single server, which it has its processing unit, it has its memory, it has its maybe acceleration within that server. So we want to free up those resources from their physical containment and to make them available via software to build composable systems independently of their location in the system. So obviously for that, interconnect is very important. How large that area where different components are located can be depends if we are using electric connection or optical connection. Again, we are hitting the physics, and in order to provide no latency, and there are plenty of what is the kind of low overhead protocol for interconnect that we should use to realize these systems. So composable systems are currently a big topic. Many of industry leaders are working on it, looking into how to create them. Everybody is moving towards that. They are not here yet, right? So first we would kind of offload memory, then we would offload accelerators and so on. But 2 years ago at a panel sponsored by the government, general feeling was, and expectation was that within 10 years, all systems will be built like composable systems. So why is everybody so eager to build composable systems? First of all, we have kind of great flexibility in how to use those resources. We are freeing the stranded resources. In the past, memory used to be very inexpensive. Over the last decade, it became almost as expensive as compute resources. So frequently, memory is stranded within a server currently where it is not being used, whereas on some other server, applications are starving and cannot get enough memory. So it would be great if we could take this memory, create a memory pool, and allow different applications to use as much memory as they need. So this would reduce our total cost of ownership. This would reduce our operation costs in cloud computing. This would increase flexibility of applications. We can provide as many resources, as many accelerators as they need for their optimal implementation. While for a cloud provider, it's easier to kind of place and locate and manage the resources available. And also, it increases flexibility for the future. We do not know what is the killer application of the future, what are resources that they will be needing. But if we can on the fly or easily create a composable system and add more resources that we need, then our response time is much better, and we can build better systems with higher computer performance, with lower time and lower cost. So if we want to continue delivering compute resources to attack always bigger problem and lower the cost of the computing, we have to do something radically different than what we were doing so far. We have to kind of start thinking not about only hardware, only software. We have to start thinking about how to bring this hardware and software together to have this harmonious collaboration and co-design and coexistence of hardware and software from the beginning, to think at the system level and in our design of the systems. So both hardware and software are part of the system. We have those different hardware components, but obviously we need smart software in the background who is going to make all those components work seamlessly together and to glue them together. We have to co-design software and hardware and accelerators. So everything is just piece of a system, pieces of puzzle that have to fit together and form beautiful picture of powerful compute systems that we can easily use. Talking about ease of use, obviously our systems are distributed within a data center. We are on what servers and what places applications and run and how data are moved around. But they have to be easy to program. Otherwise, if nobody can make a use of and program to develop great applications on top of that, its usability goes down. And this all comes to that we have to kind of significantly change and rethink how are we writing software and how all of these pieces are fitting together. Since I would like to just very briefly mention cloud computing and how cloud computing is fitting in this image of a new era of computing. And what it does is basically, if this is a roller coaster of slowing down of moves, and we are figuring better ways how to use existing hardware, and we are figuring out new ways how to add more specialized hardware, then on this roller coaster, cloud computing is giving us a kind of a seat in that and not suffer all those twists and turns. Because if cloud computing figures out, a provider can figure out and use those integrators, various accelerators, and make use of them, a user of the applications and developer will automatically get advantage of all those advances in building computing systems without themselves having to be exposed to all the gritty details. So in addition to delivering huge scale as large as needed, and providing all those data insights of using them, it's also needed this open ecosystems where everybody will come together to build this system It cannot be done by one corporation, one company. It has to be done in an open source ecosystem in collaboration. Since we are talking about future, I just have to mention sustainable computing and our responsibility that we have towards the future of computing. At Google, I'm talking about climate change and computing sustainability. At Google, we want to go to 24/7 usage of carbon-free energy, and to work with the local kind of industries and companies where data centers are located, to be smart about choosing the location of data centers and try to, you know, that a data center is using huge amount of energy, more than small towns and cities. So this is obviously a huge chunk of the energy produced is going worldwide for computing, and we want to make it as good as possible. And it's actually on us. So I talked about these challenges and talking about Moore's law. What they say, when there's a challenge, there's an opportunity. So we have plenty of opportunities in front of us. I'm giving here, listing here a couple of pictures of the giants of computer architecture and computing. In addition to Moon, there's Dinar, who actually worked for IBM, and two of them are describing differently scaling, technology scaling, building always smaller transistors and scaling up of integrated circuits. Then we have here von Neumann, who both describe von Neumann architecture and so-called von Neumann's bottleneck. Here's Maurice Wilkes, a giant who pretty much defined caching for computing architecture, and I'm including Amdahl as well. You know about Amdahl law. It's not directly architecture, but it is talking about system, about balanced system, that just improving one part of the system will do only so much for improving overall system. So we have to consider all parts of the system and make them work harmoniously and be balanced and optimized. So with this, I would like to summarize this talk, that we are in an important time. Significant revolution is happening. New era of computing is ongoing, and after 10 years or more of it, it's kind of evident now that it is happening. And this is once in a generation opportunity. It's caused by end of Moore law, which is caused by end of scaling or difficulties in continuing using technology as we know it. And new trends are emerging, not one but multiple. It's about heterogeneity and about composability. And we are currently reaching critical points to make a huge difference. Hardware and software are just parts of the system. We have to consider all components of the system, and boundaries between them will continue to blur. And with this, I would like to thank everybody.